Hello, kids. Right now we're going to go over complex numbers, which most of you have probably seen before, but I'm going to remind you how they work. So, we have a complex number is written in the form a plus bi, where a and b are real numbers, the ones that follow the rules that we're used to and have known for all of our lives. So, whenever you have two complex numbers, to add them together, I'm going to call that a1 plus b1i plus a2 plus b2i equals a1 plus a2 plus b1 plus b2 all times I. Boom. You now know complex addition. Same is true for subtraction, where you could say, honestly, I'm just going to do it more quickly than that. Instead of writing it out again, I'm going to say a1 plus b1i minus a2 plus b2i equals a1 minus a2 plus b1 minus b2 times I. Following that, we're going to get a little bit more complicated in multiplication and division, especially division. So now we have a1 plus b1i times a2 plus b2i. This gives you, if we use the distributive property, a1, a2, no parentheses, plus a2, b1. We're about to attach an I to a bunch of terms real quick. You can find them by doing a2b1 plus b2a1. I is attached to both of those things. Plus b1 b2i squared, but we have I is defined as the square root of -1, so b1 b2i squared is just the same thing as negative b1 b2, so we're going to say minus b1 b2. So that's just using the distributive property and the fact that I squared is equal to -1. Now we're going to get into division, which is actually going to make things a little bit more tricky. Actually, first we're going to go over something called the complex conjugate. The complex conjugate of a number a plus bi is denoted with a little bar that goes over top of it. And it's equal to a minus bi. It's the number where when you multiply them together, it's going to give you a nice real number equal to the magnitude of a plus bi squared. And before I get to that, I've got to show you what a magnitude is. So the magnitude of a plus bi is, if you remember the Pythagorean theorem, the square root of a squared plus b squared. And actually, I'm just going to go ahead and write that. It's going to be written with absolute value bars, if you remember those. A plus bi. So it's basically the size of it, in the same way that the magnitude of -5 is 5. The magnitude of 3 plus 4i is the square root of 3 squared plus 4 squared, which is going to be 5. But now we have this conjugate, which is something of the same magnitude as a plus bi, but when multiplied with a plus bi, gives you simply a squared plus b squared. So let's actually show that that's the case. A plus bi multiplied by a minus bi gives you a squared plus A, B, I minus A, B, I minus B, I squared. Now, we remember that I squared is equal to -1, so let's go ahead and get rid of that and turn this negative into a positive. And A plus BI minus, or ABI minus ABI is going to be 0. And whoops, that's supposed to be a squared. So that all is equal to A squared plus B squared. Now, another useful thing about this when it comes to division is that whenever you want to divide by a complex number, its complex conjugate is going to be the nice way to turn things into real numbers. That may sound a little confusing at first, but I'm actually going to go ahead and erase the top so that we have a little bit more space to do this work. I'll put this on the board in just a moment here. We have A1 plus B1I over A2 plus B2I. Something we can do is to multiply by the conjugate of the denominator divided by itself so that it's equal to 1, but gives us the nifty properties of real numbers. So it becomes basically a multiplication problem. So we can go ahead and say A2 minus B2I divided by itself, which of course equals 1. So we then get the product on the top. So we can just FOIL that out. A1, A2 plus a few things multiplied by I, which are A1, B2, sorry, A2, B1 minus A1, B2. Times I. And we again have the B times B term with the double negative. So we get plus B1, B2 divided by, we just did the whole conjugation thing down here. So we get A squared plus B squared. Sorry, A2 squared plus B2 squared. And we can actually represent these. You've seen that we have a coordinate axes grid right here. But if instead of considering this as x-axis and y-axis, you actually considered the x-axis as the real number line, and we consider the y-axis as the imaginary number line, which basically means that a 2 on the y-axis would be considered 2i. We then have a point like 2, we have 2 comma 3 equals 2 plus 3i, and so on, which when you use something like 3 comma 4, you can really see with more certainty that the whole magnitude of that we used before is actually the length of the line you need to draw from the origin to that number, because that's 3, 4, square it. You've got the Pythagorean theorem telling you that's 5. So let's do one quick example before calling it a wrap. Let's say that we have 2 plus 3i divided by 4 minus I gives us, we can multiply by 4 plus I over 4 plus I, and we end up with 16 plus 1, so 17 in the denominator. In the numerator, we have 8 plus 12i plus 2i plus 3i squared, which is minus 3, giving us 11 plus 14i over 17. And that pretty well covers most of the properties of imaginary numbers that we needed to go over right now. So have a good one.